This lecture is a continuation of the first lecture of the series Introductory Concepts, namely lecture IN1A. We will discuss coordinate system. A portion of this topic will be covered in this lecture and would continue further in part 3. Let us start with what we call handedness. You might know that 90% people are right-handed, that is, feel more comfortable to do things with their right hand, while 10% of the people in the world do the same things comfortably with their left hand. We can use our left hand or right hand to assign x-axis, y-axis and z-axis in order to build a coordinate system. Accordingly, we have two types of coordinate systems. One is left-handed coordinate system and the other one is right-handed coordinate system. There are 4 rules to identify the handedness, and they are the finger rule, the curl rule, palm push rule and the screw rule. One should note that if these rules are followed with right hand, we have a right-handed coordinate system, but if these rules are followed with left hand, we have a left-handed coordinate system. Here the encircled dot represents a direction which points towards the reader away from the plane of the paper, that is, in this direction. This is my left hand, and let me use the finger rule first. Thumb pointing along x-axis, the index finger pointing along y-axis, and the middle finger is pointing along z-axis. So this is a left-handed coordinate system. Next, the curl rule. This is the left palm. Place the palm over x-axis and curl the fingers along y and outstretch the thumb, then this will be the z-axis. So this is a left-handed coordinate system. Next, the palm push rule. Thumb along x-axis, fingers along y-axis, and the palm is pushing towards z-axis, which is up. Next, the screw rule. This is the screw, and if it is rotated from x to y with the left hand, then it will move along z-axis. Having finished analysis with my left hand and identifying this as a left-handed coordinate system, let me try to apply these rules to this coordinate system with my right hand. This is my right hand. According to finger rule, thumb will be along x-axis and the index finger will be along y-axis. Now this is the middle finger, but it points down. But this coordinate system has a z-axis pointing up, which means the z direction is not obtained with my right hand properly. So it is not a right-handed coordinate system but a left-handed one. Next, the curl rule. I place my right palm on the x-axis and curl fingers towards y and outstretch thumb. Here thumb indicates direction into the paper and not towards the reader away from the paper. So I do not get the correct z direction with my right hand. The palm push rule. This is the right hand. Thumb along x-axis, fingers along y-axis. Now the palm pushes down. It indicates a direction downwards, which is not so for this coordinate system. The screw rule. If I take the screw and it is rotated from x to y, then it will go down but not up. This means that this coordinate system can be analyzed with my left hand. It matches with the orientation of the fingers of my left hand, and therefore it is a left-handed coordinate system. Let us now come to the right-handed coordinate system. I will use my right hand following these rules to analyze this coordinate system. This is my right hand, and first the finger rule. Thumb placed along x-axis, index finger is along y-axis, then this middle finger will indicate the z-axis, and it does so. So this is a right-handed coordinate system. Next, the curl rule. If I place my palm over the x-axis, curl my fingers and outstretch my thumb, it indicates a direction upwards, which is z-axis. So by the curl rule, this coordinate system is a right-handed coordinate system. Next, the palm push rule. The thumb is along x-axis, fingers along y-axis, then the palm pushes upwards, which is z direction. So palm push rule also confirms the same thing, it is a right-handed coordinate system. And finally, the screw rule. I have a screw in my right hand and rotate the screw from x to y, and if I do so, the tip of the screw advances along z-axis. So it is a right-handed coordinate system. Repeat the same things with my left hand. If I place thumb along x-axis, index finger along y-axis, then the middle finger points down, which should be the z direction. But for this coordinate system, z is up. This means it is not a left-handed coordinate system. If I put my palm on x-axis, curl my fingers towards y and outstretch the thumb, then the curl rule using left hand shows it is not a left-handed coordinate system because z is up but my thumb is pointing down. So it is a right-handed coordinate system. Next, the palm push rule. The left thumb is along x-axis, fingers along y-axis, the palm pushes down, but z is up, which means I do not get the correct result with my left hand. And finally, the left-handed screw, if I move it from x to y, it is actually not screwing up but unscrewing. The screw goes down, the tip moves down, so it does not indicate the z-axis. So it is clear that the left-handed orientation does not match with this set of coordinates, so it is not a left-handed coordinate system but a right-handed one. The axis of the coordinate system matches with the orientation of the fingers in the right hand, and so it is a right-handed coordinate system. Let us now try to interrelate the left-handed coordinate system and the right-handed coordinate system. Certain coordinate systems have been shown, and let us check their handedness first. So testing this one with my left hand, if I curl my fingers from x to y, the outstretched thumb is z-axis. So this is indeed a left-handed coordinate system. Again, if I attend this one with my right hand, if I curl my fingers from x to y, the thumb indicates z-axis. So this matches with my right hand orientation. So this is right-handed coordinate system. So left-handed coordinate system, here we have right-handed coordinate system. Now what about this one? So I can check with my right hand again. So this matches with my right hand orientation, so it is right-handed coordinate system. And the last one, let me test with my left hand. So again this one is left-handed coordinate system. So the result which we got is, this is left-handed coordinate system, this is right-handed coordinate system, this is right-handed coordinate system, this is left-handed coordinate system, and this is suppose a mirror. Now this transformation from left-handed to right-handed or from right-handed to left-handed can be accomplished with the help of a mirror. So if we place a mirror here, it takes us from left-handed to right-handed or from right-handed to left-handed. We can show it by placing a mirror in reality. Let me introduce a mirror across this line. So this is left-handed coordinate system, and there you see a right-handed coordinate system. This is a right-handed coordinate system, and here you see a left-handed coordinate system. So this mirror has transformed a left-handed coordinate system to a right-handed one, and a right-handed coordinate system to a left-handed one. And the original figures, here are they. So indeed these are mirror images. Let this be the x-axis and this one is the y-axis. Now in which direction would the z-axis be? Take the right hand, place the palm on the x-axis, curl fingers towards y, then the outstretched thumb will indicate the z-axis. So this is a right-handed coordinate system. Now repeat the thing with the left hand. Take the left hand, place the palm on the x-axis, curl fingers towards y and outstretch the thumb, which will indicate the z-axis. So this is the left-handed coordinate system. So to make a gist of things, this is the x-axis and this one is the y-axis. So if z is along this direction, then it is a left-handed coordinate system, but if z is in this direction, it is a right-handed coordinate system. So this is it, right-handed coordinate system, left-handed coordinate system, and obviously they have x and y common, but z is different, which means they cannot be superposed. Let me try to superpose my left hand and right hand. At least we should make an attempt. Here is my left hand and I am placing my right hand upon the left hand. Clearly the middle fingers match. Middle fingers coincide, they match, but the thumb falls on the little finger. Little finger falls on the thumb, index finger falls on the ring finger, and ring finger falls on the index finger. So the coincidence is not perfect, only one finger can be made to coincide. The same happens if we try with our left and right foot. You will be shocked to discover your handedness if you sit in front of a mirror and write something or eat. You might be right-handed, but the mirror will say you are left-handed. Or if you are left-handed, the mirror will suggest that you are right-handed. This is because the mirror laterally inverts or changes the handedness. This is my right hand and this is my left hand. Now I will put a mirror in between and take off my left hand, but you will be able to see the left hand still. And there it is. You can see the left hand, which is not the actual left hand, but the mirror image of the right hand. Because here is my left hand, the actual one, and the one which you are seeing in the mirror is not the left hand, it is the mirror image of the right hand. In physics, we often speak of handedness, not only of the reference frame, that is how is z placed with respect to the xy plane, but also we speak of handedness of a particle. Let me just refer to it. What I shall explain now is in harmony with our visualization process. But when we refer to a particle, they are very, very small objects. They are point-like, and we defined point in a previous lecture, lecture IN1d. And also a point-like structure or a particle obey physical laws that are much different, and the main point is we cannot visualize their motion. They have a dynamics, they move, they show or manifest their presence to us, but we cannot follow their motion. And such failure of us to visualize or follow their motion is a very fundamental aspect of nature. It is not that we fail to follow their movement at each and every instant due to a lack of better or powerful instruments. It is in fact a law of nature. And we are not going into those things. But it is also true that to understand or realize some fact, the best thing is to visualize the movement with the help of our senses: touch, sight, hearing, smell, and taste. And this method or this way of viewing things is called a classical view. For particles, the actual movement is of quantum mechanical nature that cannot be visualized, sensed, or felt, or seen. And we are not interested with those things in this lecture. We just present what we call a classical view. Let us make a specific discussion of handedness with respect to two particles. One is called neutrino and the other antineutrino. Again, movement of a particle is described by specifying two things. One is linear movement, that is change of position with time, and this is denoted by linear momentum, which is mass into velocity, which is not a property of the system. It may change. The other one is a property of the system like mass. it is of very intrinsic nature, called spin. And spin is an angular momentum, but mind it, it is definitely not an orbital angular momentum. In this lecture, we do not have a scope of elaborating on this fundamental or inherent property called spin, and we concentrate on the topic of the study today, that is handedness, which we shall elaborate using two quantities. One is momentum, that is denoted by P, and spin, denoted by S. Classically, the term spin means rotation, revolution, or gyration, and the term spin is used in the games of cricket, table tennis, and spin is a term that is used to describe rotation of Earth from west to east with a period of 24 hours, which is called diurnal motion, that was first observed or seen by Foucault. In this lecture, we will refer to two particles. One is called neutrino, the other one is called antineutrino. And let us discuss what we mean by their handedness. And let me once again remind you that the diagrams that we present for this motion is just an imaginary model, because as mentioned earlier, we cannot trace the motion of a particle, and that is how nature works. Though of course we can trace a larger particle. Now come to these diagrams. The rule is that if a particle has its momentum parallel to its spin, we say that it is right-handed. In other words, a right-handed particle spins or rotates in such a way that its spin maintains a right-hand screw relation with the direction of movement, that is direction of momentum. Antineutrino is such a particle. Suppose this is the particle and this is momentum direction. It spins in this manner. Now check that the movement of the particle can be described with my right hand, and this is how it spins. The thumb indicates the direction of spin, and it is indeed the direction of momentum or the direction of advancement. So we can conclude that an antineutrino is right-handed. We next describe another type of motion. Look at this diagram. This speaks of a particle called neutrino that has its momentum antiparallel to spin. We say that it is left-handed. In other words, a left-handed particle spins or rotates in such a way that its spin does not maintain right-hand screw relation with the direction of movement, that is direction of momentum. So we cannot describe its motion appropriately with our right hand, though we can indeed describe the motion with our left hand. Suppose this is the particle and this is the momentum direction. Particle advances in this direction and the particle spins in this way. Now check this movement, whether it can be described with my right hand. This is how the particle spins. The thumb indicates the direction of spin, which is obviously opposite to the direction of momentum. So the movement of this particle, neutrino, is not in harmony with a right hand description, but it will fit with a left hand description as follows. This is the left hand and this is how the particle spins. The thumb indicates the direction of spin, which is identical to the direction of movement of the particle or the direction of momentum. So we conclude that a neutrino is left-handed and an antineutrino is right-handed. To an inquisitive mind, It would appear strange that we are ascribing handedness to particles, calling the neutrinos left-handed and calling the antineutrinos right-handed. This is not a childish thought, nor are we trying to decorate and put ornaments on the objects of study. The particles that are present in nature, neutrino, antineutrinos, which are particles like electrons, protons, neutrons, and so on. The aim of any theory or logic or model of science or physics is to explain and interpret experimental observation. The reason for ascribing or attaching the handedness property to neutrino and antineutrino, that is the description of a right-handed antineutrino and left-handed neutrino, is to explain a very important experimental observation which I would spell out soon. But before that, let us get acquainted with another very important term which is called parity. The word parity means equality, consistency, balance or equivalence. That is how much bias you show towards something, how much inclined we are to a particular view or thought or logic. Let us cite an example. How shall we view the population over handedness? Is it an even distribution? The world is dominated by the right-handed people, they being 90% of the population. And so we would say that there is no parity, there is no equivalence regarding handedness of the population. Nature has a bias towards the right-handers. Nature favors right-handed people. So with respect to handedness, population is not symmetric. There is lack of parity or presence of unevenness, presence of bias. With this in mind, let us attend to these figures. Consider an antineutrino which is right-handed. If we take mirror image, what we see is a left-handed antineutrino. But left-handed antineutrino does not exist in nature. So far as handedness is concerned, only right-handed antineutrinos are there. So there is a lack of parity, and we say that parity is violated. What we see in the mirror is not a real particle. Now consider a neutrino which is left-handed. If we take a mirror image, what we see is a right-handed neutrino. But right-handed neutrino does not exist in nature. So far as handedness is concerned, only left-handed neutrinos are there. So there is a lack of parity. Parity is violated. What we see in the mirror is not a real particle. This is what I have demonstrated just now. A right-handed antineutrino upon mirror inversion gives rise to a hypothetical particle because in nature left-handed antineutrino does not exist. Again, a left-handed neutrino upon mirror inversion gives rise to a hypothetical particle since there is no right-handed neutrino in nature. So these two particles are non-existent while these two particles are the real particles. It is time to make a gist and come to the conclusion. Based upon handedness, we can think of four particles, four neutrinos: right-handed antineutrino, left-handed antineutrino, left-handed neutrino, and right-handed neutrino. But nature is biased. It is not uniform in its choice of and allows only two types of neutrinos to exist. One is right-handed antineutrino, the other one is left-handed neutrino. Now beta decay is an important nuclear phenomena which is emission of electron or positron from a radioactive nucleus. Actually, at the time of beta decay in the radioactive nucleus, neutron and proton suffer mutual transformation and these particles are emitted, and along with them neutrinos are emitted. Now whenever an electron is emitted, an antineutrino is emitted. Whenever a positron is emitted, a neutrino is emitted, and the antineutrinos are right-handed and the neutrinos are left-handed. Because of the absence of left-handed antineutrino and right-handed neutrino, clearly there is lack of parity, which is called parity violation, because four types of neutrinos do not participate equally in this interaction. Only two types participate, so there is lack of symmetry. In a nutshell, the phenomena of beta decay is explained by the presence of only two types of neutrinos, right-handed antineutrino and left-handed neutrino. So handedness of particles plays a major role in nuclear beta decay. Now let us investigate if we can move from a right-handed coordinate system to a left-handed coordinate system through the technique of inversion. Suppose we make the xy plane reflecting. So this is the xy plane before reflection and this is the xy plane after reflection. They are same. Now what about the z axis? It inverts. So z goes to minus z while x and y remain same. So here in this example, one axis is inverted. Now what about handedness? This is a right-handed coordinate system, but this one is a left-handed coordinate system. So inversion of one axis changes the handedness. Now let us invert two axes. So this is a right-handed coordinate system. Suppose x-axis is inverted, so x becomes minus x and y becomes minus y, but z remains as before. Now xyz is a right-handed coordinate system and minus x, minus y and z is also a right-handed coordinate system. So if we invert two axes, there is no change in handedness. Now let us make the origin reflecting by use of a point mirror. Then x, y and z all inverts. So x goes to minus x, y goes to minus y and z goes to minus z. Now x, y, z form a right-handed coordinate system, but minus x, minus y and minus z form a left-handed coordinate system. So this means inversion of all axes or one axis changes handedness, but if we invert two axes, handedness remains invariant. Now what is parity operation? Parity operation is simply reflection about origin, or also called inversion. And under mirror inversion, as we have shown just now, x, y, z all invert. So x becomes minus x, y becomes minus y and z becomes minus z. So here is the diagram. O is the point mirror and then the vector r, which has coordinates x, y, z, is inverted and it becomes minus vector r. Due to inversion of all the coordinates x, y, z becomes minus x, minus y, minus z. So vector r goes to minus vector r. What happens to the other coordinates, for instance the angles and so on, will be discussed in a future lecture. Let me mention some great people who were left-handed and made immense contribution to the world through their talent, hard work and steadfastness. Being in hopeless minority could not hold them back, and they made their mark, and their names are etched in gold in history. Marie Curie and Pierre Curie, Neil Armstrong, Barack Obama, Ronald Reagan, Napoleon Bonaparte, Bill Gates, Amitabh Bachchan, Abhishek Bachchan, Leonardo da Vinci, Charlie Chaplin, Mozart, Lewis Carroll, Helen Keller. These are some examples of the lefties. Let me cite an interesting story that relates Napoleon Bonaparte. Ancient travelers rode on horseback on the left side of the road. As majority were right-handed people, they could hold the reins with left hand and keep right hand free, enabling them to defend themselves with a sword in case of any attack. But Napoleon, being himself a lefty, changed the rule of the road in European countries that he conquered from keep left to keep right. And the driving rules are still keep right in many countries, though here we have a keep left rule. We will now give definition of a few terms that are used in physics. One is chirality or laterality. Consider the mirror image of my left hand. In the mirror, you see an image which is the photocopy of my right hand. Now, are they superimposable? We showed that the right hand and left hand are not superimposable. Accordingly, my left hand and its mirror image are not superimposable, and similar is the case of my right hand not being superimposable on its mirror image. Actually, there is an asymmetry in the spatial arrangement, and hence object and its image are not superimposable. Such non-superimposable objects are called chiral. And if we have a molecule whose internal structure or arrangement is such that it does not coincide with or superpose upon its mirror image, we call the molecule chiral. Our hand is chiral as explained, but if an object and its mirror image are superimposable, then they are not chiral, but they are achiral. The flask shown, a cylinder, a sphere, a rectangular parallelepiped, these are objects such that they superimpose on their mirror images. So, they are not chiral, but they are achiral. Helicity is the projection of spin in the direction of momentum divided by the magnitude of spin. In other words, it is the dot product between unit vectors along spin and along momentum. Dot product will be discussed in vector calculus. Now, accordingly, for right-handed antineutrino, since momentum and spin are parallel, the helicity H turns out to be positive, while for neutrino, which is left-handed, since momentum and spin are antiparallel, helicity turns out to be -1. And neutrinos, that is neutrino and antineutrino, are nearly massless particles which travel with nearly the speed of light, and more details will be discussed in particle physics about these particles. In order to proceed further with coordinate system, we have two choices. One is the right-handed coordinate system and the other one is the left-handed coordinate system. We have to make a choice, and the choice that people make is obviously the right-handed coordinate system. And we, irrespective of whether we are left-handed or right-handed, will all use right-handed coordinate system. It should be noted that left-handed system is not wrong, but it is a convention, it is a choice that will not use it and will use the right-handed coordinate system, perhaps because majority are right-handed people. So in all cases in physics, we'll reject this one and we'll accept the right-handed coordinate system. We will accept the right-handed coordinate system. I shall end with a story of Mark Twain, who is famous for his wit and satire and was called the greatest humorist the United States had ever produced. Mark Twain was a righty, that is right-handed, but developed arthritis in his right hand during the last decade of his life. But that could not diminish his appetite for writing more, and he taught himself to write with his left hand and continued with his literary work. So Mark Twain was born a righty but died a lefty. I'll end this lecture with his quote, "The secret of getting ahead is getting started." And finally, the man whom we call Mark Twain had the real name Samuel Langhorne Clemens, and this Mark Twain was his pen name. Thank you.